Welcome to Chapter 5 and Section 5.1. In this chapter, we're going to be looking at the concept of an inner product and an inner product space. We're going to see the kind of basic definition in this section, look at some examples of them, see what we do with them, what are some properties that they have, and we're going to see throughout the chapter how we use them. So to start us off, we're going to go right in with the definition. So let V be a vector space. An inner product on V assigns to each vector U and V in the vector space a number given with this notation of U and V. So notice we use the kind of triangular brackets here. You probably saw back in Calc 3, we typically use the triangular brackets to represent a vector. In linear algebra, of course, we said in previous chapters we don't use those anymore. We use just parentheses to represent vectors now, and we use context to dictate when we know it's a vector versus a point. The reason we do that is because we need these triangular brackets to indicate that an inner product has been taken. So an inner product assigns to each vector in the vector space a number such that the following four properties all hold. The inner product of a vector with itself should always be greater than or equal to 0, and equals 0 only if the vector itself is 0. The inner product of U with V should be equal to the inner product of V with U. The inner product of CU comma V, so if you have a scalar times the first component U, that's equal to C times the inner product of U with V. So you can pull constants out of that first component. And the inner product of U1 plus U2 with V is equal to inner product of U1 with V plus inner product of U2 with V. So we can split the inner product by addition as well within that first component. Now, if we take V, our vector space, to be Rn, define the inner product to be the inner product of two n-dimensional vectors as the sum of the products of their corresponding components, so a1, b1 plus a2, b2, etc., all the way up through an times bn. This is what we call the standard inner product. Of course, this is something that you have seen before back in Calc 3. This calculation was known as the dot product on Rn. So the dot product actually is a specific example, a specific case of an inner product. So a lot of times we will have these standard inner products that we like to use for a given vector space. This one is very common, so assume for Rn that this inner product is used unless otherwise stated. So if we're talking about taking an inner product on Rn, we should assume that they mean the dot product unless we say something otherwise. If you want to verify products of the dot product, so like for example, so if we check property 1, so we take a vector a1, a2 through an, inner product with itself, or dot product with itself. We multiply the corresponding components and add, so that's a1 squared plus a2 squared, yada, 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 all the way to an squared. Every one of these terms is squared, meaning that the sum will be greater than or equal to 0. Right? It will always be positive or potentially 0, but it will only be 0 if every single one of these terms is 0. Right? So we say and will equal 0 only if a1, a2, etc., all the way through an are 0. Okay, so the inner product, or the dot product in this case, produces a number that is greater than or equal to 0 that will only be 0 if all of the values in the vectors were 0, right? In other words, if the vector was the 0 vector that went into it. Okay. The rest of these properties, these are properties of like vectors that you've seen back in Calc 3. So 2 through 4 left as exercise. So these proofs are of the same level as something that you would see in Calc 3. So you're more than welcome to give those a try, but you'll see that they do work out very similarly. So taking a look at a different type of vector and a different type of inner product, we have the vector space of C, so all continuous functions on the closed interval from a to b, so this is a function, all functions f, such that inputs on the interval from a to b produce real numbers, and these functions are continuous. Okay, so the C represents continuous, the interval from AB represents all inputs, and we output real numbers. Define the inner product of any two functions f and g within this vector space. Define their inner product using this integral. So if we want to evaluate the inner product of two vectors, we would run those vectors through this integral on that interval from a to b, and we would get out a numerical value. And that numerical value is the inner product. So let's just check our four conditions here. So if we take inner product of f with f, we get integral from a to b of f of t squared dt. And this, with that square term in it, of course, is going to guarantee us a value greater than or equal to 0 and equal 0 only if f is 0. So that's the only way we're going to get a 0 out of that one. If we take inner product of f with g, that's the integral from a to b of f of t times g of t dt. And the properties of integration and algebra allow us to switch these in order. And this, as written, is the inner product of g with f. So property 2 holds. For property 3, if we take our constant c times f, so we get our integral of c times f of t g of t dt. Rules, again, of integrals allow us to pull the c out to the front. We get f times g. So this is c times the inner product of f with g. And property 4, we have f1 plus f2, inner product with g. So that's integral of f1 of t plus f2 of t times g of t dt. And of course, we distribute. So we get f1 times g plus f2 times g. And then again, using integral properties, we can split up across addition. So we get our f1 integral and our f2 integral. So that's inner product of f1 with g plus inner product of f2 with g. So the fact that all four of those inner product properties hold gives us that this does define a valid inner product. Okay, so we can then use this as again, a valid inner product on this vector space because it satisfies all four of these. If it didn't satisfy even one of them, then we would not be able to use this as a valid inner product. Now, looking a little more conceptually and geometrically at the idea of an inner product space, we can compute length for a vector using inner products. So this is the length, or another word that we use is the norm of a vector. Now, of course, we should be pretty used to the concept of computing length of a vector in like Rn or R3 specifically from calculus. But of course, we can apply this to any vector of any vector space if given a valid inner product. Note, so here the norm of the vector is given by the square root of the inner product of the vector with itself. And note, if the length or norm of a vector is 1, we call V a unit vector. Again, a concept that you should have seen in Calc 3, coming back recontextualized. So consider the vector space R3, so the one that we should be the most familiar with. If we take the square root of the inner product of a vector with itself. So we're using standard inner product here, so the dot product. So if we were to take the length of a vector, say ABC, this would be the square root of inner product of ABC with ABC. So we take the dot product, so that's going to be A squared plus B squared plus C squared. And naturally, this is the formula for length of a vector in R3, right? It's based off of the distance formula. Okay, so like, for example, if we wanted to find the length of the vector 2, -5, 3, for example, we would take the square root of 2 squared plus -5 squared plus 3 squared. We would get rad 4 plus 25 plus 9. So we would get radical 38 would be the length of this vector. Now, when it comes to vectors that have been scaled, so when they're multiplied by a scalar like we have down here, the length or norm of a vector times a scalar, that's the same thing as the square root of the inner product of CV with CV. When you pull out the C, you can only pull out from one component. So we would pull out the C from here. We would switch the order, pull out the C from there, and then you could switch them back. But that would give us a C squared out in front here, which when you take the square root of that produces an absolute value of C, and then still the formula for the length of V. Okay, so the length of C times V just multiplies whatever the length was by the absolute value of C. Okay, so we can pull out constants like that. We just have to take their absolute value. Now, looking at this a little more conceptually, it's an interesting example. So we know the length of V is 2, the length of W is 6, and we know the inner product of V with W is 3. And it's asking us to compute the length of this new vector, W minus 2V. So in order to compute this, so I get length of W minus 2V It's going to be the square root of the inner product of the vector with itself. Right. Now, this is where the inner product properties can help us in starting to simplify this down. So we know that in the first component, we can split up across addition, and we can also factor out constants. So that would include the negative and the 2. So what we can do, we can split this up. So we'll get a w with a w minus 2v minus 2 times the v with the w minus 2v. And that successfully splits the first one. What we would then do is we would need to switch the orders of these so that we could do the exact same thing to all of the second components. But the effect that this has is essentially the same whether we keep it in the first or second component, and that's definitely something we could prove. We could prove that these properties can be applied to the second component using proper methodology. But essentially what happens with something like this is it basically just kind of foils itself out. So if we split these across addition, subtraction, and pull out the constants, and then reorganize it, so put it all back in its proper order, so we end up getting inner product of w with w minus 2 inner product of w with v. So that's this one. Then minus 2 inner product of v with w, and then plus 4 inner product of v with v. And again, it's kind of interesting the way that it works out. It does look kind of like a foiling problem. So like if you think like first, outer, inner, last, like that. So we get w with w. We get 2wv right here. We get 2vw right here. And we get 4vv right there. Now, we want to go ahead and put this in a form that's going to help us with these. So we want to know, because we know that the length of v is 2, the length of w is 6. What we can do is rewrite this a little bit. The inner product of w with w is almost the length of w, except the length of w would be this vector with a square root. So this, in its current form, is length of w squared. And again, because I'm not touching this square root out here, that's outside of kind of the whole problem right now. So then we've got minus 2vw, minus 2wv minus 2vw. We can go ahead and apply the second inner product property that allows us to switch the order of these and make them both the same. So we'll get minus 4v with w, and then plus 4 times inner product of v with itself, again, will be the length of v squared. And now these are all things that we know in the problem. So it was a matter of simplifying this down algebraically to get it to a point where we could then actually solve and put it in terms of what we know. So this is going to be 6 squared minus 4 times 3 plus 4 times 2 squared. So that's 36, and 4 and 4 is 16. So that's 52 minus 12. So that's the square root of 40. Okay, or 2 root 10 if you like. But that would be the length of this new vector w minus 2v, found without ever knowing exactly what w and v are, but just by using properties of the inner product and the predefined values here. Now, if we have a vector that is non-zero, we can form the unit vector u, which is just taking the vector v divided by its own length or its own norm. Again, a concept that you see in Calc 1 when you're talking about physical vectors in 2D or 3D, but this can be applied to any vector space given a valid inner product. So for this example down here, given a vector space of continuous functions with inputs on the closed interval from 0 to 1, the inner product of f and g is the integral from 0 to 1 of f times g dt. What is the length of e to the t? E to the t is a function, right? It is a function with inputs on the interval from 0 to 1, so it is a valid function on this vector space, and so we can perform this inner product on it. So the length of e to the t is square root inner product of e to the t with itself. So we're going to get square root integral 0 to 1, e to the t times e to the t, so that's e to the 2t dt. Take the antiderivative of this, that's going to be 1/2 e to the 2t from 0 to 1. Careful, the 0 case does not make a 0. It actually makes e to the 0, which is 1. So we get 1/2 times e minus 1, all within the square root. And that would be the length or the norm of the vector e to the t, given the vector space of those continuous functions. So moving on from length, we can also define the angle between two vectors v and w, defined by the inner product of v and w equals length of v times length of w times cosine of theta. So again, another formula that you would have encountered in Calc 3 that we know applies for vectors in R3 and R2, but we would want to, see that it works for any vector space. This we could solve for theta, and we get theta is the inverse cosine of the inner product of v with w over length of v times length of w. The Cauchy-Schwarz inequality says that the length of the inner product of two vectors is less than or equal to the product of their individual lengths. This tells us that the inputs of this cosine have to be on this interval from -1 to 1 because this numerator here is going to have a length less than or equal to the denominator. We can use properties like the Cauchy-Schwarz inequality and other properties such as the one we're going to look at right now, the triangle inequality, and see some of these inner product properties at work. So the triangle inequality, this is one that you would see back in geometry, but you might not necessarily put it into this context. But it says that the length of v plus w is less than or equal to the length of v plus the length of w. So as a triangle, we get 3 sides with our side V, our side W, our side V plus W. What the triangle inequality says is the length of the hypotenuse side, the length of this longest side, is less than or equal to the sum of the other 2 sides. Okay. If it was equal to, that means that these two would be exactly, so like V would be here and W would be here. They would all coincide with each other if it was equal to. If not, the sum of these two will be greater than or equal to this side. This is the property that basically confirms the idea that a straight line is the quickest way to get between any 2 points, right? If you're walking along a path from point A to point B, and you have like one path that goes straight there in a straight line and other paths that go kind of at an angle or at a corner, this side will have a length that is less than or equal to the sum of those sides. So we're actually going to be able to prove this using the properties of the inner product. So we're going to start with the left-hand side, sort of. So we're going to get the length of V plus W. And we're actually going to start with it squared. The reason I want to do this is because if we don't, then everything that we're about to do is going to have square roots in it up until the very end. So we'll just start with it squared, but you could absolutely still do the proof without the square there. But this gives us the inner product of V plus W with V plus W. That expands out or foils out, if you like, to inner product of V with V plus 2 inner product of V with W plus inner product of W with W. The first and last one, inner product of a vector with itself, that's just the length of that vector squared. And the vector VW in the middle there, the reason that we get an inequality showing up in this property, this is where we can actually use something like the Cauchy-Schwarz inequality. This says that the length of V with W is less than or equal to the length of V times the length of W. So we know that this is going to be less than or equal to length of V squared plus 2 length of V with W squared plus length of W squared. Oh, I'm sorry. I wrote that wrong. That's 2 length of V, length of W. There we go. So this is where we get the inequality showing up using again, that Cauchy-Schwarz inequality. And from here, we have something like, x squared plus 2xy plus y squared, right? If you just envision those in like variable form here, this is something that is actually factorable. So this would give us the length of V plus the length of W squared. So if you look at all we have here, we have the length of V plus W squared is less than or equal to all of this. So let's set that up right here. And now we can go ahead and take the square root of both sides. So we get the length of v plus w is less than or equal to the length of v plus the length of w, which is the triangle inequality. So a very geometric property of triangles and lines, proven using the concept, the very general concept of an inner product space, being applied to any vector space in general, right, with any vectors in general, v and w. So this is more of a universal property, not just geometry of a couple of lines in the xy plane. But that brings us to the end of section 5.1.